Okay. Next step, we discuss more of the fundamental of the bending. So, okay, if you have a beam or any element that has a lateral force on that or the bending moment on that and it bends, how would be the strain on that? How would be the deformation? How would be the stress, and learn how to calculate it? Now the next step is that, okay, if we know how to calculate them, then how can we design it? So the next step is that we want to design the beams, so those are the basics of that, or the elements that's under bend. So this chapter basically talks about that, how you are gonna design a member that's under bend. The thing is that when you want to design the beam under the bending, you need to know where is the maximum bending in that element, because the bending is not going to be uniform. In the previous example, it assumes that you have a uniform, in the previous section, it assumes you have a uniform bending, two bendings in the entire member. But it's not the case. Usually the bending, we had the shear and bending diagram with the statics, and it usually shows that the bending change in the entire beam. So if we want to design it, we have to find out where is that maximum bending happening. So there are two ways of doing that. The one way that first I'm gonna review that is that the way that we did in the statics. So you start to cut the member from the left to right and calculate the bending at any given section. And then we draw the diagram, and then we can figure out where is the bending. That's the just the traditional method. Is the tedious. There's lots of work. Then I will gonna teach you some techniques that you can draw the bending and shear diagram much faster without doing all those cutting the members or the beam. So you can. Usually, in most cases, you can just look at the member and just draw the both shear and bending diagram, then you get the maximum. So let's start from the so the basics of what we had in the statistics. So we know if one of those methods that I'm going to teach you doesn't work, or you get confused, so you can always use the original method to work with them. So it's the shear and bending, shear and moment diagram. Take it one more time. If we want to draw the moment diagram to find the maximum moment in the beam, then so we can design the beam for that given point. So just very quickly, a reminder of what we had before. If I have a beam like this, and there is a force applying somewhere on that beam, assume there's a force applying here. If I go ahead and cut it to see what's the internal force somewhere here, so I can go ahead and cut that. So it is the A, B, and then point C. So at point C, if I cut it, it's going to be look like this. That's it. Section A, C. And then I have the section CB. And the positive internal force, I'm drawing that, so when we get to drawing, you know. The positive one for the normal force was the tension. The tension was positive for the axial force. For the shear force, is positive if going down on the left side and going up on the right side. And for the bending, so these are the positive, axial load, shear load, and the moment. So the entire point is that what we want to do is that we want to go for now, we want to calculate we want to design it for the bending. So we want to find the moment diagram, but usually to find the moment diagram, you have to find the shear diagram, and then from there find the moment diagram. So we're going to learn these two. At the moment, we don't care about the axial load. We don't want to do that, so we are going to leave it for now. So let's start with a simple example. Go ahead and show you how we do that. So the very first simple example is that if you have a simple span beam, simple supported beam, with the force right at the middle of that. So and the method we are using for this one is the same as for almost every method we are going to use. So have a simple beam A, B, and there is a force right in the center. So there is a force right in the center of that. F, and assume this is the half a L, this is the half a L. Remember that the distance between the two supports in the beam, it calls a span. So if, for example, in the problem you might see that the span of the beam is L. It means that the distance between the two supports is L. So the first one that we have, remember that when we have something like that, the very first step was go ahead and find the support reaction to do that. Good. So first step, we want to know that yek. So one, support reactions. So for this case, I'm going to spend, so we know that the AY is half a F and AB is half a F. If it was not like that, we have to write the like the statics, we put all the equilibrium equations, find them. Then the second is that establish x-axis starting from left end of the beam. So we are going to establish the x-axis starting from there for the entire problem. So this is going to be my x. So it start from the very left and it goes there. And then we are going to, the third step is cut the beam between forces or in the middle of distributed load to find internal forces. So the first step that look at here, I have is the A and B. So I have half a F here. I have So look at here, between the forces, so I have one force here, so I have to cut it once between A and the middle of the beam, and once between middle of the beam and the end of the beam. So let's call it, if this point is C, so once between AC and once between CB. So for the first section, that's gonna cut it is that if the X is between 0 and half of there. So that's the first step. So if I have that, eventually you probably get there, you don't need to draw it, but I have, for now we'll draw the beam. So I'm gonna have it somewhere here. So it's gonna be point A, so I have there, and then I have the P, the V, and the M. So if I have that for that specific space, and then the distance from here to where I cut it is the X. So sigma fx is 0, it gives me the p is 0. Sigma fy is 0, it gives me the v is half a L, and sigma m is 0. About, usually we write the sigma m about where we cut it, but we can write it from anywhere. So it gives you the m is half a f times x. So if you look at your, in that span, the f is constant. Sorry, the v is constant, the m is functional. X. Then the next part is that I have to cut it between the C and the B. So the X is going to be between so the X is going to be between half a F, half a L, and a L. So if I cut it between there, so it's going like that. And then I have the half a F here. I have the F right in the center. The X would be from the beginning to the where I cut it. So that's the point A. That's the C, and that's where we cut it, and then we have those forces. I put the P for this one, but for the rest of the example, I'm not going to put the P, so we are not going to calculate it anyway. There's a P, there's a V, and it's the M. So again, if I go ahead and write the sigma fx is 0, that gives me the P is 0. If I write the sigma fy is 0, so I have F going down, half a F going up, so the V would be half a F in the opposite direction. And then I have the sigma m is 0, about, usually about where we are cutting. If I look at that, the m, so this distance, this is x, and then this is the half of the. So if I write the moment about that point, the m would be half of the f times the x minus f times x minus half of the f. So the m would be, first of all, the m would be this one, so half of the f times x minus this distance, which is going to be x minus times f. So that's going to be the f. That's going to be the f. And then, so now that I have this equation, the next step is that I have to go ahead and draw them. So if I this is a beam. Try to fit them all under each other. So this is a beam. That's the F. And then I have this one's going to be the V, and this one's going to be the M. So for the if I want to draw them for the points A, B, and C. So A, C, and B. So from here, if I draw the V between A and C is plus half a V. So it's gonna be plus, it's constant. So it's constant half a F going ahead. Then from middle of the beam to the rest of the beam is going to be negative half of the F. So it just drops down from here and then goes back. So it's going to, so that's the shear driver. And then what we are interested in is the moment diagram. So we want to see where it's going to be the maximum. So M for the, if we draw that, so if, because you have the X, you have to go ahead and substitute the X with the value. So if you put the X 0, it gives you 0. Put the X half of the L, because go to the middle. So it's going to be FL divided by 4. So it goes from the 0 to FL divided by 4. So it goes from here to here, which that value is FL divided by 4. And if you draw the other part, if you draw that one, it will goes from here. If you put the 0, it will goes back to, sorry, if you put the L, it goes back to 0. That's gonna look like that. So if I looked at that, I would say, okay, the maximum moment happened at the center of the beam, and the value is the FL divided by 4. So that is the moment I have to design the beam for. So that's this very simple example. So any example we have, that's the basics of what we are gonna do. So we start to breaking the beams in the middle of the force, between the force, or in the middle of the distributed load. And for each section, we will find the equation, and eventually we draw them, and then when we draw them, we will find what's the maximum on the graph. Another example, let's look at the one with the distributed load. So if I have a beam like this, and there's a distributed load of W on that. And again, here everything is parametric. In the exam or the problem, you get all of them has numbers on them, so it's not going to be X and L and W number. So if there's a distributed load of W on that beam, so I want to see what's the shear and moment diagram on that. So one thing about this one is that if I start to cut it, from the left and go to the right, you get here, it's important. If I start to cut it from here and go to the right, because my X, I'm going to establish the X here. I cut it and go to the right, and only look at the left section. There's no reaction in that left section, correct? So I don't need to find the reaction of the support. If I do find it, it's not going to hurt you, just you are calculating something that you're not going to use it. So remember that if you are cutting and you keep the part that doesn't have a reaction, you don't need to calculate the reaction at the first step. Here in this one, there was no way that I cut it and I'm not ended up using the reaction. So, then we establish the X. Again, the X is gonna be from the very left of the beam. So the 0 is always there, and the X is up to the point that we are cutting. So I have only one distributed load. I need to cut it somewhere in between them. So it's gonna be the X would be between 0 and L. So the X would be between 0. So if I cut it between 0 and L, what I'm gonna get is something like this. So let's say point A. I have a distributed load. Distance from here, that point is X. And the internal force that I'm going to look at it is going to be the V and the M. Again, you can put the P there, but it's going to be 0. So if I have a distributed load, I have to replace the distributed load with the equivalent single load. Remember that, do not replace the distributed load which is equivalent before cutting the beam. First cut the beam, then replace it. So if I go ahead and replace that, the force that I'm gonna have here is gonna pass through the centroid of the load. So the location of the force is at the centroid of the load. So I know that if this is the X, this distance is going to be half of a X and half of a X. And the value is the area under the load. So the area under the load is, this is W, the height is W, the length is X, correct? So the magnitude would be W times X. So that's the magnitude of that load. And the distance for that is going to be sitting right in the middle. So that distance is half of the X. And that distance is also half of the X. Now if I go ahead and write that sigma fx is 0, sigma fy is 0, so it gives me the V is Wx. If I write the sigma m is 0, usually as I said about this point, so if I have the sigma m is 0, m would be Wx times, so it's going to be W, so it's going to be half of W, half of Wx. Sorry, the V would be negative. Now I can go ahead and draw them. So if I go ahead and draw those here again. shear and the moment. It's going to be the V. It's going to be the moment. And then I have the end of the beam, so I just mark that point. So if I draw the V is negative Wx, so you get the V star from the 0, and when it's L, it's going to be negative WL, so it's going down like that. And so when you get to that point, it's the negative WL. So at that point, it's negative WL. For the moment, if you draw that, it's gonna go like this. And at that point, it's gonna be negative for level square. So also, that is going to be also the moment will be negative. It's going to be negative. And negative come over x squared. Any question? So just remember, when you're dealing with the distributed load, do not replace it with the single load until you cut it. After you cut it, replace it with the single load, but not before. And it has another example, just very quickly, the mention, I'm not gonna do the entire thing, just very quickly mention how it works. So, next example, the book. The beam, that's gonna be the point. So it's gonna be So if you want us to analyze that, again, the first step is that we have to go and write it very quickly. We want to get to the next one, but the reaction of the support at the B, RB would be 40, and R at D would be 14. So if you do calculation, you will find those for the reaction of the support, and then we have to cut it. So how many times do I have to cut that? So I have to cut it between these two forces, and between these two forces. So I have to cut it 3 times. So I have to cut it somewhere here, I have to cut it somewhere here, I have to cut it somewhere here. So if I'm gonna again establish the X at the very left side of the beam. So first time the X would be between 0 and 2.5. The second section would be X between 2.5 and 4. 2.5 and 5.5, and then it would be the X between 5.5 and 7.5. So I have to cut it in 3 sections. So it would be, the first part would be like this. So I have 20 here. V M. The second part would be like this. So there's going to be 20 here, 40 here, and again V and M. And the last part would be so I have the 20 here, I have the 40 here, I have the here, and then I have the V and M. This is 46. This is 46. 46. Again, for each of them, the X start from the very beginning to the where we are cutting it. That is 2.5. And this if I do that for each of the section, I'm just gonna write the values. So here we would be sigma fy 0, so we would be negative 20. Sigma m would be 0, then m would be so the minus for the x. And the same things here, sigma fy is 0, so we would be 46. 21 is 46, yes. And then sigma fy is 0, sigma m is 0. Then m would be, if you have it here, so it's going to be minus 20 times x plus 46 times x minus 2.5. And then here again sigma fy is 0. Then it's going to be, we would be 46 minus 20 minus 40, and sigma m would be 0. Then again here you have m is negative 20x, plus 46 times x minus 3 plus, negative minus 40, and the distance is x minus 5.5. So you can just go there and then start to draw. V and M. Double check those formula. I think they should be right. So if you go there and put numbers in those equations and draw them, this is what we're gonna get. Get minus 20. You have to start from negative 20. Let me draw those points. Go up to 26. Then drop down to negative 14. So if you put numbers in those formula, if I have them correctly, this is what you are going to get. So for example, for the first one, if I put the x0, it's going to be 0. If I put the x 2.5, it's going to be negative 50. Same for this. If I write the equation right, it should come so that's negative 20. 46 times. This is x minus. Is 2.5. So it's going to be 46 x minus 2.5 and the 40 x minus 5.5. So these are the way that we are doing it in traditional way that we learned it in the stats. Now, as you see, you're gonna get what you want, but it's gonna be real time consuming, lots of calculation involved. So the next step is that I'm gonna give you some techniques that it works for most cases, so you can use them to simply draw this shear and moment diagram without need to draw all those calculation and equation. As I said, in most cases, most examples, you can just draw them very quickly. So, the relationship between load, shear, and moment. Shifts between load shear so the very first relationship is that if I have a beam that has a distributed load on that, so if I have a beam like this, simple beam that has a general distributed load on top of that. So you have a distributed load look like this. I have the information. So the very first relationship that we know is that if the dV over dx negative double. In other words, what's the dV over dx? The slope of the line. So dV over dx is basically a slope of the shear curve. Let's say slope of shear curve. So the slope of the shear curve is negative W. So that's the very first relationship that we use. The second relationship is that if I choose any 2 points there, I call it C and D. any 2 points. Assume I go there and say, I choose 2 points here, C and D. V at D minus V at C is equal to negative area under the load between C and D. So it would be negative of area under load curve between C and D. So, if I want to write that at this very simple way, it will tell me what's the delta V?
D minus C.
Area under the curve.
Yeah.
Minus area under distributed. So change in the shear is just change in the air is equal to area under the load, and it gives you how this is gonna make your life real easy. I'll show you how. So that's the very important equation as well. Then what we have is the dm over dx, dm over dx is equal to v, where dm over dx is the slope of the moment curve under distributed load. Then again, the m at D minus m at C would be equal to area under shear curve between C and D. So then I can write it, the delta M would be area under shear curve. So if I draw a line here, these two. These are the two equations. That's very important for me. So a couple of points here. If the load curve is nth degree, then the shear curve would be n plus 1 degree, and the moment curve would be n plus 2 degree. So look at here. The shear is linear, the shear is constant, then the moment becomes linear. If the shear is linear, the moment would be parabola. So if it is whatever is the degrees of the shear, the moment has one more on that. So the first degree, if it is function of x, the moment is function of x squared. Okay? If the shear is the x squared, the moment would be x cubed, and so on. That's the first things. The slope of shear curve. So the other one is that the slope of shear curve is negative W. The slope of moment curve is V. So steps to draw shear and moment diagram. So the first step is that or the not this steps probably the so if we have concentrated force, the shear diagram moves up or down in direction of force equal to amount of the force, to magnitude of the force. So if we have distributed load, shear diagram okay moves up or down in direction of the load equal to area under load. And the moment diagram changes equal to amount of area shear curve. And then the moment diagram is 0 at end roller or pin support. Remember that end is important. So if it's in the middle, it doesn't. So I'm gonna use these points just to draw the curve without cutting it at all. I'm showing. So they might seem confusing, but they're gonna make it really easy to draw the diagram. Let's look at a couple of examples and see how it works. For this one, I don't have a number because I'm just going to make it up, so probably need to help with calculating. So I assume the load on that is, I have a distributed load, let's say 10 Newton per meter. Point A, point B, and the distance between them is going to be 5 meters. So first step, I have to find the reaction of the supports. So I have to replace that with a single load, which would be 10 times 5, which is going to be 50. So it's going to be 25 here, 25 here.
So the triangle with the line underneath it, that's a roller support?
Yeah, the one that has a line in it is the roller, that's one's the pin.
Okay.
Agree, up to here? So, now that I have them, I want to do the calculation right. So, the first step was the first step. If I have a distributed load, I'm gonna move in the direction of the load equal to amount of the force. So I'm gonna draw so it's a V. So, the first step, for the V. At point A, if I'm at point A, I'm at point A. At point A, I reached the concentrated load. What was the rule for concentrated load?
Shear diagram moves up or down in the direction equal to the magnitude of the
So,
force.
so the concentrated load is
Going
up. So my shear curve will going
up
up. How much?
by 25.
25. So my start points would be from here, I go up to 25. Now, what's the for the distributed load?
Moves up or down in the direction of load equal to area.
Under the curve. So that's one. And then the load was the is 0 degree. It's constant. So the shear should be
Just 1 degree.
1 degree. So it should be in line. So it should be line that going, the load is going down, correct?
Yeah.
So it should be a line that going down because it goes in the direction of the load. It would be a line going down. How much it goes down? Equal to the area under the curve. So if it starts from 25, how much the area under that curve?
Um,
10 times 5. So area under that would be
50.
50. So it will goes down 50. So if I start from 25 and goes down 50, how much I would be here?
Negative 25.
Negative 25. So I will end up negative 25 here. Linearly going down. So that's your shear.
Does it, so like right now, you have that red line at the ending going back to 0. Is it meant to go back to 0 or is that just to like show that?
Because if you cut it right at there, 0.
Oh, okay, gotcha.
So you got it? You don't need to cut anything, you don't need to write any equation, you don't not need to write any equilibrium. As long as you know those rules. Not a moment.
So it's gonna be not a quadrant, it's gonna be an exponential.
So- So the first one is going to exponential. So no, not exponential. It's going to be second order. So the first order is going to be second order, and the magnitude is going to be equal to the area under the shear curve. And then I know that's going to 0. So look at here. I have the support at two ends. I have a support at both ends. Remember that if it was not at the end, that rule doesn't work. But because it is at the end, it's at the end, the moment at those points are 0. So that's the first, so I know that I start from 0, end up 0. And then the area under the curve, how much is the area under the shear? So from here to here, how much is the area? What's the area here? I don't have those numbers.
31.25. Divided by 2, 'cause it's a triangle. I did that.
So is that half of 2.5 times 10? How much is that?
Oh, yeah. Well, times 10. So 312.5. Oh, 2.5. So 31.25.
Sure. 31.
Why is it times 10?
So this distance is 2.5.
Yep.
Also that's 25, sorry. You're right. This distance 2.5, so it's 25 times
2.5.
2.5. I got 2.5 times 25.
Yeah, and so that's 31.25.
31.25. Is that correct? So that area is 31.25
So that's what our moment is.
positive.
Yeah.
So the moment goes from 0, look at here, delta M is the area under the shear curve. So area under the shear curve, the change is positive 31.25. So it goes from 0 to
31.25.
31.25 with the degree of
2.
2. So I know that I have to, when I get there, it's going to be 31.25 and second degree. Now from here to here, from center to here, how much is the area down here? It's got negative of that. So if it's plus, it's going to be negative 31.25. You agree? So now the change from here, look at here. The change from here to here should be negative 31.25. So it brings me from positive 31 to 0 again, second order. So it goes from there to there. So that's going to be my moment.
So you mentioned that this doesn't completely work if there isn't a roller or pin at the end. What do we do in those situations?
If it is not, I think we have example I'll show you.
Okay.
If it is assume instead of this being here, it's gonna be there.
Yeah.
Then I cannot just assume this is 0.
Okay.
So I don't know at the beginning that it's 0. So I have to add them and minus them and see what I get when I get to that
Okay.
point.
Sounds good.
If it is at the end, I just right away I can put 0 there. So any question about that? So I want to make sure that you get really good at that method, because I don't want you sit and try to calculate the shear and moment by just cutting and cutting and cutting. So when you get used to that and you know what you're doing, you probably can draw the shear and the moment in less than 5 minutes, very quickly.
So I mean, in those cases, we're gonna have to know how the load, like the slope of the curve for the load, though. So, okay, yeah. Is that normally gonna be a thing that's given, or is that something we're gonna have to figure out?
Which part?
The curve of the load.
This one? It's
So like the 10 newton meters, yeah.
Yes, it's given.
Okay.
So here it's constant. If it's, for example, function of, usually it's constant, but if it's function of the x, so for example, it would be 10, for example, it would be 0 here, 10 here, so you can calculate the equation of the line.
Yeah.
So whatever is that is going to be one order above that, and it's going to be one order above the previous one. So let's look at another examples. So another example is a curve. So it's a beam that goes from, so you have a support here and a roller support here, and those distances 8, 10, 8, that's the A. What do we do? B, C, D, and E. And then we have the concentrated load on these two ends. We have the B here. At the B, we have 20,000 pound. At the C, we have 12,000. And here we have distributed load. £1,500 per foot. So I want to draw the shear and moment diagram for it. Again, the very first step is that we have to go ahead and find the reaction of the support. So because I don't want to spend time on that, I'm just going to put the reaction of the support there, but you know that we have to find the reaction of support. So if we put it there, here I'm going to get 18,000 going up, and here I get 26,000 going up. So now I want to draw the curve, so I'll go ahead again like the previous one. M. I want to bring those points down, so it's going to be okay. Now I want to start from the shear. Start from the left. I get to the concentrated load. So the shear move in the direction of the load equal to amount of the load. So the shear goes up 18,000. Okay, so the shear goes up. Let's see. Make sure that it's correct. So it goes up 80. So it goes up to 80. So I say 18. I don't put the 1,000 there. Then I go ahead, I get to 20,000 down. What happened?
Go down in the straight line like 20.
So it goes down 20. So I will get to what?
Negative.
So I will get to the negative 2. So it's a plus 18. I go down 20. So I get to negative 2. Then there's nothing there. I will keep going until I get to C. C again, going down how much?
Like
12. So it's gonna be
Negative 14.
negative 14. So it will go down to negative 14. Again, there's nothing between them. It goes as Now at the D, what happened?
Up 26.
Up 26, so negative 14 plus 26, I will go to
Positive 12.
positive 12, so I will go up to 12. Now, from D to E, distributed load. So the distributed load is downward, so I'm going down. The distributed load is constant, so I'm going down linearly. Because it's constant, so I'm 1 degree more, and we go down linearly. How much I go down? The area under that load.
1.5 times 8 is 12.
So it's a 12. So 12 linearly going down will means I go back to 0. So I'm gonna go back down. You got it? Now the next step is the moment. So I know the moment A is the, look at here, A is the end support, simple support. So the moment would be 0. At the D, it's a simple support, but it's not at the end, so we don't know the moment there. So I know the moment before I start, this is gonna be 0 at that point. And then the area under the curve. So how much is the area here?
So 18 times 6 is 108.
So 108. Let me write it so you know where it comes from. So it's gonna be 18 times 6 plus 108. So I will go up 108. With what degree?
Second degree.
So linearly, I will go from the 0 to 108.
Not linearly.
It's constant.
Oh, that's, yeah, okay.
It's constant, so it will be
Yeah.
linear. So we'll go up, for example, assumes here. So we'll go up to positive 108. Then area here is, how much is the area here?
Negative 16.
Negative 2 times 8, negative 16. So I will go down negative 16. So 108 minus 16, how much is going to be? 92. So I will go down to plus 92. So that's where, so where that 92 comes from. So it's going to be 108 minus 16 is going to 92. Now, how much the area here? It's going to be negative 12 times negative 4. Times 10, negative. Negative 140. Correct? Yeah. So now again, I have to go down 92 minus negative 140, which takes me down to negative 40. So it goes down to somewhere here. So it's going to be 92 minus 140, which would be, how much is that?
Negative 48.
Negative 48. So it's going to be negative 48. Now, here, what's the area here?
48.
So it's going to be half of 8 times 12 is 48. So it's 48 positive. So it's going to be negative 48 plus 48 would be 0. With what degree? No. It is linear. So it's going to be second degree going from there. So it's going to 0 here. So it goes from second degree from here to here. And it's going to be minus 48 plus 48 would be 0. Question? Let's look at one more example so we get make sure that we know what we're doing. We'll write it here also so we know that. So it's going to be 31.25 minus 31.25, so it would be 0. So you know where it comes from. Last example. The book has more examples. I can look at it, but probably I'm not going to have time. Let's look at this last example. So again, remember that before I forget, if the simple support is in the middle, then the moment is not 0 there. And look at that. If I want to design that beam, where should I design it for? Point B. So that's where I get the maximum moment. So if I design it for there, it's gonna survive and the rest of it. So the last one is gonna be a beam. So it has a simple support here. Simple support here there. Gonna be 6 meter here, 3 meter here, and this is A, B, C, and then I have the kilonewton per meter going. Kilonewton per meter, it's going like that. So I want to draw the shear and moment diagram.
That's the only force.
That's the only. So again, the very first step, I have to go ahead and find the reaction of the support. So I'm not going to, that statics part can do it easily, but if you do it, you get, at A, you get 80 going up, 80 kilonewton, and then at C, you get 40. So, okay, the same things, I'm going to start to draw them.
Is that 40 kilonewtons or just 40?
There's a 40 kilonewton.
Okay.
Then I have the moments going on. So we start from the shear again. At the A, we have 80 going up. So it starts from the positive 8. So it goes up there to positive 8. Yeah, for example, as soon as 8. So that's the start point. Now, between the A and B, what happened?
Goes down 120.
Goes down 120.
Second degree. straight line 0.
So load is constant, so it goes down, because it goes down, how much the area under the curve as a line. So it goes to, what would be that point, sorry?
It's gonna go down to negative 40 because it's going down 120 in total.
Negative.
Since we started the speed.
Draw those lines as well. That becomes negative 40. So it goes to negative 40 linearly. So it's going to be 80 minus 20 times 6 would be negative 40. Is that correct? So it goes down to negative 40. So what will happen between B and C?
Nothing.
So between B and C, I have nothing, so it's going to stay negative 4D. Because nothing happened there. And then what happened at C? Goes up 40. That becomes negative 40 plus 40 would be 0. And you know that by looking at that, you know that, for example, this shear 0, 0, so there. Any question? For the moment, again, I have the simple support at the end. So the moment would be 0 at those ends. So I know that the moment would be 0 here, and the moment would be 0 here. Now, between the A and B, what happened between A and B?
It's gonna go up 240. Well, wait, between A and B.
So the things that there's part of that is positive, part of that is negative. So I'm gonna put that point there as well. So this part that is positive, how much is that?
240.
Half of 80 times,
6.
no, the 6 is the entire thing.
Oh, 3.
So if it is 80, it is 40, it's going to be 4, correct? This is going to be 4. It's going to be 2. If these two wants to be proportional. This is 2 times of this, correct?
Yeah.
So this should be 2 times of that. If it's the height is 2 times, so the base should be also 2 times because they are proportional. So it's going to 80 times 4, which would be how much? Plus
160.
160. And down here, how much is that here?
40. Yeah.
So this area is going to be negative half of, so half of negative 40 times 2 is negative 40, correct? So from here to here is positive, so the moment going, look at here, from the A to that point. So it goes from 0 to 160. With what degree? Second degree, because it's the first degree, so it's going to be second degree. So it goes up to from 0 to 160. So it goes up to 160. So it's going to be 0 plus 160, 160 here. What happened from here to B? So it goes from 160 minus 40, which would be 120. But again, the second degree. So when it gets here, it's going to be 160 minus 40 would be 120. And then from here to here, how much the area of this is negative 40 times 3 is the negative 120. So it goes from 120 minus 120, it goes back to 0. It goes back. But what degree? Linearly. Because it's constant, so it goes down linearly. It's going to be 120 minus 120 would be 0. So I would make that rules to probably it's better word. So any question about any of those? About this method? So this is the, in any of the problem you are doing, this is the method I want you to use to find either the maximum shear or the maximum moment for the design you want. Like that, there's nothing wrong with what we learned in the statics, but just too time consuming.
Shouldn't we focus on which point on the line is farthest from 0? Because that one is going to be like the maximum bend.
No, it depends on the span. It depends on the supports. So you look at here, you have the maximum moment here, which is very close to the support. Here you have the maximum moment. There's no way that you can look, you have to draw it and see where would be the maximum moment.
I guess if our graph ended up having like the one, that middle one, the max is positive 18. If at one point it went to negative 20, wouldn't that be a more, like, wouldn't that put a stronger type of stress on the support, on the beam?
We looked at the maximum absolute value.
Okay, so it's that.
So if it's negative, instead of bending it like this, bending it the other way.
Okay, so it is absolute value.
So it's the maximum absolute value. That's what we use it for the design.